yesterday we had this nice reception, so I guess all of you going back home, you ask yourself, how about vortices in higher dimension, right? Then you had a nightmare. Okay, so let me release you and have good dreams. So let me say what's happening before going to the third lecture, which is about Landau-de Gennes. So let's stick with the vector fields. In Landau in higher dimension. Okay, so as I said, so we still have a vector field defined in a ball in Rn with values in Rn. Okay, so this is the ball of radius r and r, and n is the dimension higher than 2. Okay, so the energy this one, and then just think of W to be T squared over 2, but any convex potential like this will work. Okay, so what is the boundary condition here is the vortex of degree 1. Okay, so of course you can do everything, but by multiplying with some orthogonal transformation, right? And in fact, these are the only boundary condition that we can impose in order to have some symmetry in your solutions. Okay, so that's you can check the paper, the first paper of Gustafsson speaking about this. So this means that, for example, if you think to the transformation x to minus x, right? So there you could get, for example, in odd dimension, degree -1. Okay, but yeah, in general it's only degree 1. So right, and this is what we always call the hedgehog, right? So you point like this. So this is the r, right? At the boundary, you point in the normal direction. Okay. So okay. So what is the vortex solution? So it has the same structure as in 2D. So let me call it UR of x, which is f of modulus of x, x over modulus of x. Okay, and so this profile is the same. So you remember that when in 2D, when we had degree d, that this was like a power of radius. So here the degree is 1, so you are linear, and then you go like this to 1. Okay, so of course you have an ODE, which is, so it's the minus Laplacian in since it's radial. And okay, so here you have to check that right when you will plug it in such a solution, you have to compute gradient of x over modulus of x, and that's exactly n minus 1 over r squared. Okay, so that's right. If we hit here the linear part, okay, and then you have f w prime 1 minus f squared. So this is in 0r, and then the boundary condition is f of 0, 0, right? Because in some sense you want to kill the singularity in 0. And the boundary, this boundary condition will tell you that f is 1 in R. Okay. So what is the result? So with the boys, we proved the following. So in dimension n higher than 7, this solution is the unique global minimizer for every R. Okay, so at my knowledge, this is the first result that completes the full spectrum of R. So you remember in 2D, the problem is still open because so it was that result for R large that is due to, which is the difficult one, which was due to Pascal and Rivière, and for R small, when you get convexity, that's it, right? But there is a gap where you don't know what's happening. Okay, but in high dimensions, and sometimes life is easier in high dimensions, you can prove that this is the unique global minimizer of E under the boundary condition, and what is important is for every R. And open question, what's happening in dimension between 2 and 6? Okay, so we work on it. And last year with Luc, we proved that in dimension 2 to 6, our solution stays local minimizer for every R. So in some sense, this is the generalization of Mironescu and respectively Lieb-Loss theorem from dimension 2 to dimension 3 and 6. Okay. So in dimension 2 to 6, UR is a local minimizer for every R, right? So we still don't know, for example, if in the full range, U of R is a global minimizer. Okay, so let's go to line fields. If you have questions. No questions. Good. So let me go now to lecture 3. You know, it's always like this, right? You don't finish and then you give it to the next one. So here I will stop. You will send from that. Okay, so lecture 3 is defects in Landau-de Gennes. So Ginzburg-Landau will be GL, Landau-de Gennes LDG. So defects in Landau-de Gennes theory model in 2D. So I do only 2D. Arghir, maybe we will have time to speak a bit about the 3D model. Okay, so what's the difference? Yeah, I will always make right, because now you are familiar with vector fields, so now we will have line fields. So I will always play. I like football. So we will play football between Ginzburg-Landau and Landau-de Gennes. Okay. So what do we have here? Here we have vector fields. That's in defects, right? When you look at it's the team, right? The players in the defense, middle, forward. Okay. So let's see. So here are line fields. Okay. So we saw that. So I'm speaking 2D. So here we saw that vacuum manifold, so we're in some limit vector physics like to say, is S1. Right, and here Arghir mentioned to you that this will be RP1, right? So the projective space that you could see like S1, and there is an equivalence relation that is like the group of two elements. Okay, so here if you have a field, then here you should look to so you should right. I mean in Landau-de Gennes you have molecules and you don't want to distinguish between head and tail. So therefore this should be the same, right? So that's exactly one. And this you can see as a tensor, right? Which is a 2 by 2 matrix that is symmetry, right? And spectrum is 1 and 0. Okay. Now pictures, right? So our favorite field, right? Which is also I theta, right? If we write it in polar coordinates, right? So it's the hedgehog, right? Okay, so so this is smooth as a function from S1 to S1. So here you can speak about the degree. Okay, so what you do is that you make a turn here and you look how much turn you have in the target, and here you will see that the degree is 1. Okay. Let's see what's happening for the line field. So light field, I don't have any orientation. So what you do is that you just erase the orientation, okay? But then what you see? You see that this one is the same like this one, okay? So this means what? It means that if you look at this as a field from S1 into RP1, so right, you make a turn here, then on your RP1 the degree is louder. 1/2. No, I do once, I finish RP1, yeah? And then I do twice. 2. Okay, so if you think to the formula I wrote to you, so here it's what? The degree. It was what? It was the volume of S1 times the Jacobi of U, right? Okay, but this is what? So it's always the volume here. So here you have twice less your volume. So that's why from here to here you will always have a factor 2. So don't believe if in what I write I say half integer degree. Well, think more to an integer that you multiply by 2. Okay. So degree theory plays only with integer. Okay, so that's why, okay, so here what we will see the full, right, I mean the fundamental group of RP1 is Z, right? So you have not only even numbers, but you have also odd numbers, which will give you something that is not smooth in S1 when you look to the vector. Okay. So this is what we call point defects of half integer degree. So again, read what I mean, not what I want. Okay. So from what is next, always D will be 1 over half z. Okay. So sometimes I will write b as k over 2 k in z.
Question, if you could, just trying to clarify my intuition about this formula. So this dividing by the volume, that's dividing by the volume of the target?
Yes, this is what I wrote yesterday. You took the notes, Stephen, didn't you? Oh, that student. You don't want to do like this. Okay, so. Okay, so what right so this will sometimes will be not smooth, right? So if we think to d equal 1/2, then what's happening? So you start like this, then you will turn. Okay, so you will reach here, and then you will so you turn like this, and then sorry. Yeah, okay, right? Right. And here you see you will have a jump. Yeah, for this you start. Yeah, so this is the jump. But now when you look to U star the tensor, so in RP1, then you erase the arrow, and then everything fits fine. Yeah. So this is good. So if here, right, the winding number, because winding number you can always pick, right? I mean, you make a turn here, and you look how much turn you do on the target. So see here, you went from here to here. So you did only half of the circle, right? So the winding number here is it's d, right? It's 1/2. But here, the true degree in RP1 is 1. Okay. So that's what is called singularity of degree d. This is, so here 0, from this, it's a defect of degree. Okay. So let's go now to, so this is a simplification, right? Because as Arghir showed to you, you have Q tensors that where these line fields live in R3, right? That's the physical space. So let me give you a bit about this Q tensor.
Sorry, just one other thing. Do we divide by 2 here to get a half? What? Do we divide by 2 for this second one? We're saying you divide by the volume target.
Yes. Right. So here it's 1. So the volume of RP1 is, Stephen?
There's a half of the
which is pi. Okay, right? This is 2 pi. Right? So in order to get to this one, you have to multiply. So there's a factor 2, right? So you have to multiply this by 2. Yes. So this what it is this transformation. You should be careful what transformation you put, right? But what is important is that that's the factor 2. You multiply, right, from degree 1, you go to degree 2. 2 tensors. So you remember that was relate it with the second moments in that probabilistic setting, and you look to the deviation, to the identity, which is the isotropic state. So from where you get the liquid. Okay, and that was the set of matrices that are symmetric, trace zero. Okay, so there you have 5 degrees of freedom, so it's dimension 5. Okay. So classification. So you will always understand these two tensors by the eigenvalue. So of course you have a symmetric matrix in R3. Then all the eigenvalues are real. And the fact that trace is 0 is that the sum is 0. Okay, and how do you distinguish is when all of them are equal. So of course they should be equal with 0, and there your matrix is 0 because it's symmetric. Okay, so this is the isotropic state. Okay, then you have the uniaxial. So 2 are equal, the other is not. So this is the uniaxial state. And what is the form here? It will always have this form. Right, so n is at 2, and is what is the eigenvector respectively with respect to the that distinct eigenvalue that is related with s. So what you do is you multiply with m. You see that that will give you a constant times m, and the constant is lambda 3. Is 2/3 s. Okay, and then of course the others two, since they are equal, they will be -1/2 of this, right? And then they will correspond to eigenvectors that are orthogonal to n. So living in the orthogonal plane to n. Okay, and now you have. So how many degrees of freedom you have here? Well, n is in S2, so 2 degrees of freedom, and S is another one, so here you have 3 degrees of freedom. Degrees of freedom. Okay, and the last one is the biaxial one. And here, what is the shape? So of course here you should have the sum of 2 uniaxial states. So this S and R, you see that there is always a relation between the guy here with respect to the eigenvalue coming from n. So they are different. And these are orthogonal, so they will also be eigenvectors. So they are orthogonal. Okay, and so in S2 again. And so n is the eigenvector. So again, you multiply with n, and you keep something from here. This is 0, and something from here. So the eigenvector of lambda 3, that is So search S minus R over 3. M is the eigenvector of lambda 2, which is 2 over 3 R minus S over 3. And then you sum, and then right, if you take the cross product, yeah, so the cross product, this will be an eigenvector of lambda 1, which is minus R plus S over 3. Yeah, so the sum should be 0. Fine. Correct. And I don't want to pay over here. Yes. Okay, so how many degrees of freedom here we have? So this is 2 degrees of freedom. This would be 2 degrees of freedom, but you have this connection, so you lose 1 degree of freedom. So that's 3, and then 5 from here, right? So that's the full space. So the full space S is given by these biaxial tensors. Okay, so here you have 5 degrees of freedom. Okay, let's go to calculus of variation, function of minimizers, PDs. If you have questions, I'll try to answer. You know, maybe I buy this when I go home. It's very good, I think, to wash the windows. You know, I think the German professors, they are really good for that. I don't know if they practice. And they are my guests if they come to Toulouse. Good cassoulet, but then also some practice on my windows. Okay. So, Landau-de Gennes model. Okay, so, okay, I forgot the numbers. Valeria, please excuse me. So, so Landau-de Gennes model. Okay, so I stick to D. So, our Q tensors, so they are, if you want, they are maps developing the Q tensor set. Yeah. So they are defining the ball in the disk with values in the set of Q tensors. And the energy is this one. And bulk. So that's the elastic term. And that's the bulk term. It's written. Okay, and so we always consider this kind of reduction. Well, I mean, when I spoke with, so I worked a lot in this micromagnetic model, and so when I always speak with physicists, is, for example, how they choose anisotropy, or so they said, well, you know, the anisotropy, well, it's a function, and what we do is that, okay, it's like doing Taylor development, and then we just look, okay, if we take just the first term, what's happening? Then if the model is well posed, consistent with the reality, then we can add another one. Okay, so I think in physics, this is also what they do, right? So they look to the Taylor expansion around the zero state, which is the isotropic, and then they look, okay, if they get enough physical meaning by looking to that model, then it's fine. And I think this is what's happening, right? I mean, you could take, I think there are models when you take here the 6th order development, but here we take only the 4th order. So Arghir already told you about the meaning of this. That's related with the temperature. So this means that we look to temperature below temperature where the material becomes liquid. So that's phrase squared minus b raised to third. Take the third, take the trace, and then you have the 4. Okay, so in everything that I speak, these are strictly positive. Okay. So, football game. In Landau versus Landau-de Gennes. So, defense. WU, right, that was our potential, was something that is 4, right? And here you have the path potential. Okay, so what was the minimum of this? So the vacuum manifold is at 1. So here, right? So that's the minimum. You remember? That was this double well potential. Yeah. So when you look to here to the minimum of this, yeah, as Arghir mentioned to you, it has they are uniaxials, but with the fixed, like you fix your eigenvalue. Right? And okay, and this S plus, this has S plus is the minimum. So what you do is that you plug in F bulk of such a thing. So you have like a function in F bulk of S plus if you want. And when you look what is the shape of that, so this is not positive, right? So, but it has the form like this. So 0 is which is the isotropic one, is still a critical point, but then you have something like this. And this is the minimum one, the S plus. Okay. And in fact, if you want to be like this one, at the same level, this one should be 0. And that's why you see that this is very similar, right, to the Ginzburg-Landau, because this is like U squared and the U4. Yeah. So that's why this is Ginzburg-Landau. Okay. So dimensions, really important dimensions, because right. So you saw that here we have 5 dimensions, right? In Ginzburg-Landau we had only 2 dimensions, right? So here you hope to have much more variety of things, right? You have much more directions where to go. So the dimension of this is 1, and the codimension of R2 is 1. Now, when you look to these ones, right, the dimension of S3 is 2, because this S plus is this one, so it's fixed, so you have only 2 degrees of freedom, and the codimension is 3. Yeah, because we live in the space of dimension 5. Okay, so what do we want to do? We want to look to minimizers with respect to boundary condition, like we did in Ginzburg-Landau. So what will be the boundary condition here? Here is the equivalent of right, is what we want to see, right? We wanted to see that kind of behavior, right? So it's like imposing that at the boundary. Okay, so let's impose that at the boundary. So that will be so it's at this S plus, so we want to be in the vacuum manifold. Right? And who's this? Well, this is our favorite vector field, right? Which is what I call that U star X, right? Which is that one, ID theta, but we are in 3D, so you have to give him, right? So this is 2D, yeah? But you are in 3D. So in some sense, you are on the equator of your sphere, to this sphere. Okay? Recall D is always D over 2. Right? So it can be integer or could be half. Okay, so what do we want to do? What is our aim? So is to study the minimization of our energy on the boundary condition. And again, the three questions we always ask: existence, again, is okay. This is coercive, this is coercive, semi-closed, semi-continuous with respect to H1. You get minimizers, and every minimizer, right, satisfies your equation. So, which has the form minus a squared q. So that's the linear part. And then you should be careful because you work with the trace 0, so you have a Lagrange multiplier, which is this one. The fact that trace is 0. And then, one second. I'll take my beer. And C2 Q over Q squared. So, okay, if you compute, okay, the trace of that, or right, which is like the trace of this, you get that this is 2/3 S plus squared. If you remember here, I said to you, how do you get regularities? That every solution to the Ginzburg-Landau has this kind of maximum principle. Of course, it's a system, so you cannot get it for every component, but you can get it for the modulus, and the modulus is less than 1. Okay, so for this Landau-de Gennes system, you have a maximum of principle for the trace. So you will get that this trace is less than this. Okay. And from there, you get you can do right, you can do bootstrap. Okay, so again, it's C infinity up to the boundary, and again, you can do analyse if you want. So that's the regularity and the solution. And now the tricky thing: what can you say about the limits? So you can play the same kind of game, right? That we played with Ginzburg-Landau. So when R is small, again, you have here like Poincaré inequality, right? So you have your first eigenvalue of your Laplacian. So that will be huge when R is small, right? And then, okay, here you have something. What is important is that's the R power R3, R4, and then right, if you put a parabola, if the parabola is quite large, then you get convexity and uniqueness. Okay? So if R is small, then your energy is convex, strictly convex. And then the minimizer that you find there is the unique minimizer, right? So you have uniqueness. R large, this is in general open, but with a result that Arghir will speak about. So this is the theorem of the boys. It's in the case where the degree is an integer. Okay, so for E is an integer, so this means E is so when we wrote it k over 2, so that k is 2z. Okay, so you have a real degree as an, so this has a real degree if you look as like an S1 to S1 value. So in this case, you can prove that there are exactly two global minimizers. So there are exactly two global minimizers, and that's a very nice thing. So you should think to the Ginzburg-Landau problem, but from the disk with values in R3. So what's happening? When you look to Ginzburg-Landau from B2 to R3, okay, so we are okay to the balls to the disk BR, okay, because we are not doing the 1 over epsilon number. So you look to the to a big disk of radius R, and you take values in R3. In Ginzburg-Landau, what do we have? We had that we wanted that this configuration stays in plane. So there, the harmonic map is infinity. So infinite energy. So that's why, right, this energy was blowing up like a log R. But now what you do? You give to your configuration another component. Of course, it will take that component. So going in that direction is that it will decrease the energy and it will stay bounded. Okay, so that's a very nice thing that also we understood in the previous paper with the boys. Is this kind of dichotomy that happens? Is that of course for small r you still has to stay in plane because that solution always exists, but there will be an r, so like a dichotomy, after which this escaping will become minimal. So of course you could escape up or you could escape down. So that's why you have two. Okay. So this is also my recent paper with where we understand everything in dimensions for the cylinders. Okay. So, but Arghir will speak about this. So, oops. But okay, and so again, that's open. So what's happening when k is odd? That's open, and the conjecture is that when k is 1, so when you have 1 over 2, we believe that that you should have uniqueness. Okay, that should be the. Yeah. Okay. So, but what I will do here is that in some sense I won't look to this escaping where I have global minimizer. I will look to this in-plane, so the equivalent of this in-plane solution in Ginzburg-Landau. So that's why it's a bit different. So that's with respect to this symmetry that we always okay. So special solutions, football match. Landau versus LDG. So how did we find our special solutions? We looked to group actions, right? And the group actions were given by the rotation, yeah, of angle alpha, right? So we multiplied with these guys, and we asked that our solutions, we asked that that our solutions. So when we do rotation, we get to R d alpha u of n. Yeah, so because at the boundary we turn d times, and these solutions, right? You remember they were of the form f of x I t theta. Okay. So now we want to see what are the solutions that are invariant also under this this rotation. So here d, right? So here d was a real integer, right? So here d is half integer, and okay, so this anyways, you can write whatever you want when you have chance. So you ask that your two tensor maps. So they also have to turn d times, right? But these are tensors, so therefore you have to put also r d alpha t. Okay, but what is this, right? Because this is 2d and this is 3d. So of course, what you do is, well, you complete by 1, yeah, your matrix. Yeah? Okay, so you turn only into. Okay, so the energy is invariant with respect to rotations. The boundary conditions is like this, so this is fine. Okay, but what are these? So this is a fact that it should be known even before, but so if the degree is really a non-integer one, you can prove that any solution that is invariant with respect to this symmetry here has the following form. Let me write it. Okay, this is bad because I started with E1 and then with E0, but this is our notation in the paper. So if you check the paper after, I don't want to do that. Okay, and so E1 is the singular one. So that's the n star. The n star is that one, that guy. But careful, 1/2 E2. There is no mistake there. And E0 is okay, there is always a numerology. E3 wedge, E3 minus. This is the uniaxial one. So all these coefficients in order that these are so in the Frobenius, right? I always work with Frobenius, yeah. So they are equal to 1. So what's the fundamental difference? In Ginzburg-Landau, we had only this kind of guy. So in some sense, you steady with values in S1, and then you just need to multiply with the profile that will erase your singularity in 0. The problem here is that you cannot stay on the vacuum manifold. So there is a very nice theorem of Giacomo Canevari who shows you that any solution in 2D has to be biaxial. So this means that you need to put two uniaxial vectors. Okay. So even if, okay, if you look careful, this is not uniaxial, right? Even here, this is biaxial because n star and orthogonal, they have different eigenvalues, and E3 has another one. Okay, so okay, so fine. Okay, and what's happening? What is the form of this when we get to integers? Right, so here k, that is so here you don't have this form because, right, as I told you, as I said, the minimizer should have an escaping one, so that would be a third component there. So in order to erase that, then you have to add that your solution is invariant with reflection. So if you think to Ginzburg-Landau, if you take a solution that is invariant with the third component, that you have to stay in plane there. Okay. So that's you erase the escaping solution. Okay. So then you still have the same. Okay. So then, right? So of course, so when you plug this in your equation, you will get a system of ODEs for these ones, right? Because these are solutions. Okay, and so better that let me write the energy of this QR, and I say that this is the energy in UV. Okay, so this energy has the following form: U prime squared, and now you have the degree coming up. So you recall, right, that D is always A over D. U squared, and then you have a potential. This is a polynomial that I don't want to write. Okay, this is also a constant. I don't want to write. This is a okay, that's a polynomial. You have an okay, and then so this means that you have a system of ODEs, system of two ODEs for U and V. So this is very similar with what we had. So U plays the role like our F in this Landau, yeah. So you have like minus Laplacian. Okay, and this is, so I differentiate in U, right? And then in V, I don't have this term, so I have only the Laplacian. Okay, and then you have a boundary condition. So of course, the boundary condition that we set there will fix what is U of R and V of R. Yeah. So that is okay. That's numerology. I always check S flat over square root of 2. The R is minus 1 over. This is negative. So V will be negative. And then if you look to, in order that this should be regular, so H1, then you have also that in 0, U is 0. So anyway, right? Otherwise, this is not, that's not in H1. Yeah, because you are in 2D. Okay, and due to the fact that this should be V, right, when you multiply with this should be regular, so V has to be even, so the derivative in 0 should be 0. Okay, so roughly speaking, I don't have time, but Arghir maybe will show some pictures to you. So you should see something like this. So depending, that's a very delicate theory, depending on the regime. On the regime, you look between these three things. You can ask me later or ask Arghir, what does it mean physically? So from the point of view of analysis, it's what's happening is that this become collaborative or anti-collaborative because when you take the derivative in V of this changes sign when you go from this larger and less. But there is also okay, so U will be something like this. So U is positive and increasing, but V can change. So in some regimes, okay, so V is negative. I mean, the V we know, we believe we work with are negative. Maybe you can also have things that change sign. So let me just give you a V that is negative, that is decreasing, for example. So that's V. And in fact, so this is just in the regime where before is larger than 3a squared is squared and oops, negative. And in the other regime, it becomes increasing. Yeah, it's something like this. And what should happen when you have equality? Constant. Okay. So, but I won't speak about this. So, whoops, I didn't put the theorem. So what do we know? But Arghir will help me, and this is where he stopped. So maybe he'll tell you if I don't reach everything. So existence theorem. So existence is okay. So for every R and for every degree. And so you can find an existence of humanity, and you can find a solution that is stable with respect to this radial. So in fact, it can be even local minimizer of this with respect to you can ask that U is positive and V is negative. So that's always the constraint. Then you can prove monotonicity, so such things, for every solution that satisfies this constraint, and uniqueness under this constraint, but careful, only, so it's open, but we can prove it only when we are in this region. So it's open in the other one. So we believe that if uniqueness, but always if uniqueness are within this constraint. Okay, and now the theorem is actually quite theorem, because that's right. We are always interested in what's happening with the stability in the full domain. Yes. Full, yeah. So the answer will be right in Ginzburg-Landau what we knew. So because right here the boundary condition has a degree. So in Ginzburg-Landau we knew that if the degree is 1 or -1, then we have stability. Otherwise, if R is large, it's unstable. Well, you have the same thing here. but you should know what is your solution. So the solution will be you take a stable one, for example, for the degree 1, and that solution will be also stable in the full set configuration. And I don't have time. Okay, so theorem. So this is a series of 2 papers. With the boys. So theorem. So if so let's start, right? So D is K over 2. So if K is 1, yeah, let's do only for positives, but then any solution QR, right? So this will come from some U and V, for which U and V is stable in the radial class and of course it has that sign. So any solution coming from this, then if the solution comes, then QR is stable for E of Q, right? Under this. So of course the stability there, you take the second variation. So that will give you the resistance. Okay, and if K is larger than 2, so of course write any R. Any R. Here we know that if we are on the small disk, everything is the energy is convex. So you have uniqueness. Okay, but for large R, any solution, so no matter how it is stable, unstable, anyway. So any solution, no matter, so no sign here, no sign on U and V is unstable. And exactly what you will do here, well, you know that at infinity there is another minimizer. The minimizer is the one that escapes. You shoot in the escaping direction and you kill it. Thanks.
Questions? Actually, I have a question for the first part of the lecture. You mentioned this dimensional restriction of the bigger 7. Can you comment on this?
Yes. Okay. Yes. Right. So so as I said, the conjecture should be true for any dimension. It's more the techniques we use to prove it. So the techniques we use to prove it works, in fact, for the equator map. So the thing is, you have to think to harmonic maps, to tangent harmonic maps. So in that case, the singularities is codimension 7. If you think to harmonics maps rather in the sphere, so not in the tangent bundle, the dimension of singularity is 3. But here, for the equator map, is 7. So this means that starting with dimension 7, x over modulus of x is the min, and 0, yeah, is the minimizing harmonic map. Okay, So this is related. So that's why, like in Ginzburg-Landau, when R is large or epsilon is small, you have to go to there, right? So if the harmonic map is not unique, then you cannot do anything. Okay, and so in some sense, behind that there is a hard inequality. And when you look to this, so which is related with the stability of that x over modulus of x when you do the second variation for the Dirichlet, that's positive, right? Because anyway, it has to be a global minimizer, provided that n is larger than 7. Okay, so that's so there are some, but anyway, in our problem we should get to a less dimension. So let me tell you that, okay, you know, him is great, right? I mean, we see here people, we speak. So, but I mean, now the game is who gets the answer between dimension less than 6. So, okay, we have a good method, but is restricted, okay? But then we say, okay, let's be tricky and let's not look to the full configurations that are vector fields, but the ones that are gradient vector fields, right? Because our solution is a gradient. Okay, and we had so Michael Naon is here. Yeah, so with Luke, we work on it, and we already have that from dimension 4 to 6. If you restrict to gradient fields, so in some sense that's the Aviles Giga model, if you want, in high dimension. That's true. That's the unique medium. And of course, now we work hard to get dimension 3 at least. And so that's true for every R. And now we want to get at least for R large. That is unknown. Okay, thanks.